Hi, today I want to talk about Laplace transforms and how we can use them for solving differential equations. In this video, I'll be talking about the basics of Laplace transform, how we can apply it to various functions, its various properties, and then eventually how we can use it for solving differential equations. So let's get to it. Alright, let's talk about Laplace transformation or Laplace transform as it is popularly known. How do we write Laplace transform? First, let us try to understand its mathematical formulation. Say we have a function f of t, where t is a variable and f is a function based on that variable. And we assume that this function is defined for all positive values of t. Now, if that is the case, what we do is we write an integration that starts from 0, ends at infinity, meaning all the positive values, and we write it as e raised to minus st f of t dt. And this is the Laplace transform. Here, s is nothing but a complex variable, right? Some complex variable. And when it is associated with the function, put into an integral, that forms the Laplace transform. Obviously, we assume that this Laplace transform exists, and the fact that we are doing this for the positive values of t has to be taken into notice. How do we write Laplace transform? We write it as capital L into the bracket of the function f of t, and when it has gone through the process of Laplace transform, we would then represent it as capital F of s, which then is equal to the integration. So let's look at some important formulae of Laplace transform. These are some important formulae related to Laplace transform. You can pause the video, have a look. I will talk about the derivation of a few of them so that you understand how do we apply the Laplace transform eventually, right? And all these proofs are really easy to understand. So if you understand how to do it on a couple of functions, you'll be able to do it yourself on the rest of them. So if you actually want to visualize Laplace transforms, I have put out some simple animations to help you visualize or understand what Laplace transform actually does to a function. So if we look at a simple function, say f of t is equal to 1, as we all know now that the Laplace transform of 1 would be 1 by s. So if you look at the animation, you can see that in the time domain, a constant function line is being shown, and then the kernel, which is e raised to minus st, right? How does that visualize? And when you combine them both, obviously, eventually you see that the function dies down and attains a constant value, and you can see the area under the curve as well. Likewise, if you look at maybe t, now we know that the Laplace transform of t would be 1 by s square, right? So if you look at the f of t domain in the time, so t will obviously indicate a straight line, and you know the kernel, how does it look? And if you look at their product, eventually again you would see that we are looking at convergence to a constant value. But you can see how the Laplace transform behaves or what it does to a function. Likewise, I have shown here t square. Now it's a quadratic function. You can see how it behaves. Likewise, we have e raised to at, right? And then we have sine omega t. Obviously, we know for the sine omega t, say if we have omega as the constant over here, we would have omega upon s square plus omega So my bad, omega upon s square plus omega square. And if you look at the visualization, you can see what it does eventually, and eventually hence we see a constant value. So yes, this is how Laplace transform modifies a function, right? So if we talk about a unit step, an impulse, right, at the output, you will again see the value of a constant, I mean the eventually 1, because that is what is the Laplace transform. We have ut minus a, you know, right shift, and delta t minus a. So let us look at the first one. Say we are calculating the Laplace transform of 1. Okay, so we'll write 0 to infinity 1 into e raised to minus st dt. Eventually, we can then do the integration. We will write e raised to minus st divided by minus s, and then we would put the limits of 0 and infinity. Obviously, e raised to minus infinity, right? That would eventually lead to 0, and then we can write, yeah, and then we can write all these things, which will eventually lead us to 1 by s. Hence, the Laplace transform of 1 would be 1 by s. Alright, so let us look at another example where we can apply the Laplace transform and understand how we can use the concept and look at the fundamental principle of applying the integration. So we look at another Laplace transform of a function f of t. Now this time f of t is equal to t by k when it lies, the variable t, it lies between 0 to k, and it assumes a value of 1 when it is above k. That means from k towards infinity, or above the, or rather above k towards infinity. So how do we solve this? Very simple. We write down the integration expression, meaning f of t is equal to Laplace transform of f of t is equal to 0 to k t by k e raised to minus st dt plus k to infinity 1 minus e raised to minus st dt. Alright, so this is how we can represent the function first, and then we can take the Laplace transform of individual, or calculate the integration individually, and that is how we can calculate the Laplace transform. So the first integration, if we look at 0 to k t by k e raised to minus st dt, we can write it as 1 by k t into e raised to minus st upon s, right, the first part, minus integration 0 to k e raised to minus st upon s dt. We can then substitute the limits and find out the individual values. If we look at the other part of the integration, right, which was k to infinity 1 into e raised to minus st dt. This is very simple, e raised to minus st upon s, k to infinity. We can again calculate this as well, so it's not a big deal. Now when we do all those things, we can substitute it into the final expression. I'm skipping that part directly to jump at the final solution. The final solution should turn out to be something like 1 upon k into e raised to minus ks upon s, or rather minus s, and minus e raised to minus st upon s square, and then 0 to k on one side, and then we have plus e raised to minus ks upon s. Alright, and then with the third expression, or the third fraction, if we substitute the limits, finally we should get 1 upon ks square e raised to minus ks plus 1, right? This is the final solution, and this is how one by one we can develop the Laplace transform for all the expressions. Alright, so if we move on to the properties now of Laplace transform. So what are the different properties of Laplace transform? The first property and the fundamental property of linearity. Okay, the idea here is, if you take the Laplace transform of a maybe joint function like a into f1 of t plus b into f2 of t, then what we can do, take the constants out. So we have a Laplace transform of f1 of t, right, and b plus b Laplace transform of f2 of t. So we can split them individually. That is the idea. And by taking the constants out. Now this property is a very important property and can be applied to numerous examples, which we'll see. Then the second property would be the first shifting theorem, or shifting in general, either left or right. So the idea is that if we have a Laplace transform, which eventually we represent as Laplace transform of t is equal to capital F of s, then if we multiply that function with an exponential e raised to at, the eventual Laplace transformation f of s can be shifted by one place, which is a. So f of s minus a. That is the idea, right? So if we look at this expression, what does that mean? It means that if we look at the Laplace transform of, say, e raised to at into t raised to n, alright, we can write n factorial upon s minus a raised to n plus 1. Not to forget, Laplace transform of t raised to n was n factorial upon s raised to n plus 1. So what does that mean? Simply we do s minus a, shift s by a. Or let us look at another function, Laplace transform of e raised to at sine bt. Now we know the Laplace transform of sine function. We simply shift the s by a. You can now give it a try and solve as many examples as you want by using this principle. Let us look at another example. So say we have to find the Laplace transform of cos square t. Cos square t. We know the Laplace transform of sin t, we know the Laplace transform of cos t, but we do not know the Laplace transform of cos square t. This is new for us. So let's look at it. What I do is I express cos square t in the terms of cos 2t, right? In the terms of cos 2t, I can do that. Then what happens is that now cos 2t looks very similar to cos t. It's like t but into 2. I can do something about it. So I'll rearrange the terms. I'll write cos square t is equal to half cos 2t plus 1, right? And then I'll look at the Laplace transformation of cos square t. I can write it as the Laplace transform of half cos 2t plus half. And based on the linearity property, I can write half Laplace transform of cos 2t plus half Laplace transform of 1. Now Laplace transform of 1, we know it's 1 by s. What about cos 2t? What do we do about it? Think about this. So I can write half s divided by s square plus a square. So what is a here? A is 2. So simply 4 and then plus 1 by s. Easy peasy, lemon squeezy. We have the final answer. It's that simple. Right? Now, moving on. Let us find the Laplace transform of maybe t raised to minus half. Right? Looks a little complex, but it is very simple. So first, let us write the formula. Laplace transform of t raised to n is equal to under root n plus 1. My bad. Hold on. It's n factorial divided by s raised to n plus 1. Alright. Now, if I want to find the Laplace transform of t raised to minus half, all I have to do is substitute n is equal to 1 by 2. I write those things. I write minus half factorial. I write s raised to half plus 1. Minus half plus 1, my bad. And then We know minus half factorial would be written this way, and this is simply nothing but root s, meaning root pi upon root s, or I can write under root pi by s. I'll just stop here. Simply that is the answer. Now, let us find the Laplace transform of t sine 80. Again, looks complicated, but is very simple. What are we doing? We know the Laplace transform of sine 80. We are multiplying t with it. So let's see what happens. So if we take the Laplace transform of t sine 80, we can write the Laplace transform of t dot. I represent sine now in terms of exponential. The idea here is that I can then use the linearity property and do something about it. So I express then, or I expand those terms by using linearity property and express it as the Laplace transform of t into e raised to minus it minus Laplace transform of t into e raised to minus iat, my bad, and then 1 by 2i, 1 divided by s minus a, and then we have 1 divided by s I plus I a square. Right? So it is that simple, this entire thing. Obviously, this is what I get when I do the cross multiplication, so nothing to worry about there. And eventually, it will become very intuitive once you solve more and more numericals like this. So let us look at a couple of problems that you can solve and practice, right? And you can leave the answers in the comment section. The first one would be maybe sine t into cos t, e raised to minus t into cos square t, and then maybe sine cube 2t. Very interesting cases, a little challenging, but nothing that you cannot do. So leave those answers in the comment section. Moving on. Let us now look at the Laplace transform in a different light. So if suppose we apply the Laplace transform to a derivative of f of t, so we can write Laplace transform of f dash t, right? Nothing fancy. Simply what you have to do is multiply the Laplace transform with s and minus or subtract the initial condition. This is what you do for the first differentiation, right? And in general, if you have to write, we can write Laplace transform of fn of t, meaning the nth differentiation. We can write s raised to n Laplace transform of f of t, s raised to n minus 1, f of 0, the initial condition, then s raised to minus n minus 2, f dash 0, s raised to n minus 3, and so on and so forth. We can keep doing this. What happens if we are supposed to take the integral of f of t, integration? So I would write 0 to t, f of 2t, f of t dt, and the Laplace transform of that, simply I have to divide f of s by s. It is that simple. Alright. Now, what would be the third property? The third property would be if suppose I have to multiply f of t by t. We have already seen something very similar. Or maybe a general t raised to n. We could write minus 1 raised to n d n of d is n of f of s. Simply take the differentiation. It's that simple. And this in fact could be very handy because these kind of multiplication you would often see in Laplace transforms. Now, if we look at the Laplace transform of t square cos at, and let us decide to solve it by the formula we have just learned, we know the Laplace transform of cos at is s upon s square plus a square. Laplace transform of t square cos at therefore would be minus 1 square d2 by ds square, because the second order due to the quadratic term. We have then, this expression right in front of us. We have to simply take the differentiation of s upon s square plus a square. Let me do that for you very quickly right here. A little memorization here, but yes, this works just fine, and this expression is what we get. Moving on. Let us look at the fourth property. If suppose we divide f of t by t and we take the Laplace transform of it, by this time I hope you have guessed what should happen. Pause this video and think about it. What should happen? We should simply take the integration of s to infinity capital F of s ds. That's it. It is that simple. Alright. Now, let us look at another example based on this. Say we are looking at the Laplace transform of sine 2t by t. How do we deal with this? We know the Laplace transform of sine 2t, right? What is it? It is 2 by s square plus 4, right? So sine 2t by t is equal to, we can write the integration of s to infinity. We have 2 upon s square plus 4 at ds simply. All we have to do is find the integration, which eventually should turn out to be something like this. That's it. Okay, at this point I have to delete this as well. Fair enough. Let us look at another example based on this function. We have f of t is equal to 0 to t sine t by t dt. We know the Laplace transform of sine t, right? Which is Laplace transform of sine t is simply 1 by s square plus 1, right? So we have Laplace transform of sine t by t. Then we can write simply the integration of s to infinity 1 upon s square plus 1 dt, and you know where this is going now, right? When we substitute the limits, we get simply pi by 2 minus tan inverse s, which is nothing but, you know what it is. Pause the video maybe and comment in the comment section. Now,